For decades, one single language has absolutely dominated how we interact with data. SQL. It's practically synonymous with the whole concept of a relational database, right? But what if the very bedrock of our data infrastructure is actually built on a massive misunderstanding? Welcome to The Explainer. Today we're diving into the Third Manifesto. This is a deeply fascinating study and blueprint by database pioneers C.J. Date and Hugh Darwen. We are going to explore the profound impact of type theory on the relational model and look at why we might just be incredibly overdue for a complete paradigm shift in how we think about, store, and manage our information.
So, this leads us to a genuinely provocative question. Is SQL fundamentally flawed? Now, the authors of the manifesto, Date and Darwen, they make this incredibly bold claim. They argue that SQL isn't actually a true realization of E.F. Codd's original relational model at all. Instead of a faithful implementation, it's kind of drifted way off from its mathematical roots. See, the relational model is supposed to be this formal system based strictly on pure logic and mathematics. Yet SQL, over years and years of, let's face it, messy evolution, has grown into this sprawling system full of inconsistencies, logical errors, and just unnecessary complexities. If we really want to move forward into the future of data management, Date and Darwen suggest we might actually need to leave SQL behind entirely.
Let's break down exactly why they're making this claim by running through some of SQL's notorious defects. And in the eyes of the manifesto, these aren't just minor little quirks you can sweep under the rug. They literally compromise data integrity. Take duplicate rows, for instance. A true relation is defined as a mathematical set, and by definition, mathematical sets just do not have duplicates. When SQL allows them, it breaks the core math. Then, of course, there are nulls, which SQL uses to represent missing information, and that creates all sorts of wild logical paradoxes. SQL also relies on left-to-right column ordering, whereas true relational attributes should be totally unordered, distinguished only by their name. Plus, it allows anonymous columns, like when you add two columns together in a query, and it increasingly relies on object IDs. Those are essentially just pointers instead of actual concrete values. Every single one of these defects chips away at the foundation of relational theory. To really hammer home the need for absolute clarity here, the manifesto brings in a rather surprising source. A quote from the poet T.S. Eliot, "A dog's a dog, a cat's a cat." Now, why include poetry in a highly technical database explainer? Well, it brilliantly highlights the rigid conceptual integrity you need for true database science. Think about it. A database is supposed to be an accurate model of reality. And in reality, things are definitively what they are. When we introduce sloppy logic into our systems, like nulls that mean a value is mysteriously unknown, or object IDs that merely point to a variable rather than holding a concrete value, we literally stop modeling reality accurately. Our systems need to be just as definitive and unambiguous as the real world they're trying to represent.
So how do we fix a system that has strayed so far off the path? Well, Date and Darwen proposed a really comprehensive solution, the Third Manifesto. Think of it as a formal, abstract blueprint for designing a true database management system, along with the language interface required to actually run it. The most fascinating part? It is entirely rooted in the classical relational model of data, exactly as it was first presented by E.F. Codd way back in 1969, but now it's combined with a really robust theory of types. The manifesto isn't trying to just invent a brand new relational model from scratch. Actually, scratch that. It's more like an attempt to strip away all the historical baggage of SQL and return to those classical roots, finally giving us the mathematically sound foundation future databases desperately need.
The guiding philosophy for this entire blueprint essentially boils down to this profound concept from the philosopher Ludwig Wittgenstein. All logical differences are big differences. Since a relational model is, at its absolute heart, a formal mathematical system, logic is everything. It's the whole shebang. A mistake in logic isn't just a tiny bug, it is a massive fracture in the system. That's exactly why those seemingly minor SQL quirks we talked about earlier, like allowing a duplicate row or caring about column order, are actually foundational failures. They are logical deviations from the true relational model. And following Wittgenstein's logic, those deviations are big differences that will inevitably compromise the integrity of your entire architecture. Let's look at how that strict logic applies in practice. We have to start with the absolutely critical difference between a model and an implementation. A data model is an abstract, self-contained, logical definition of objects and operators. You can think of it as the abstract machine you're interacting with when you write a query. An implementation, on the other hand, is the physical realization of that model on an actual computer system. It's exactly how the bytes are stored on a hard drive. The manifesto firmly dictates that the logical data model must remain fiercely independent from physical computer storage constraints. Mixing the two, like worrying about physical pointers or storage optimization directly in your logical query language, completely destroys data independence. The ultimate goal here is to get the model logically perfect first and let the software handle the messy physical implementation completely under the hood.
Okay, here is another fundamental logical distinction that constantly gets muddled in modern database systems. Value versus variable. It sounds incredibly simple, right? But it is crucial. A value is an individual constant, like the integer 3. It has no location in time or space, and by definition, a value cannot be updated. If you change a 3, well, it's just not a 3 anymore, it's a 4 or a 5. A variable, though, is just a temporary holder for an appearance of a value. Variables do have a location in time and space, and they can be updated to hold different values. Confusing a pure value with a variable, which by the way happens all the time when systems start relying on object IDs, leads directly to buggy, unstable data architectures.
So how do these super abstract concepts handle the sheer messy complexity of modern data? Just think about a modern relation table tracking, say, bird migrations. We aren't just dealing with simple text and numbers anymore. We might have an XML document for the description, a high-res photo, a movie file for video, audio for the bird song, and even spatial data like a map for the migration route. How on earth do we support these complex new kinds of data within a classical, rigid relational framework? Well, the answer definitely isn't to abandon the relational model. The answer actually lies in type theory. It all comes down to defining exactly what specific types of data we are allowed to keep within our relations. And that leads us directly to the concept of a type. At its very core, a type is simply a named set of values. Now, here is a pretty massive realization. The relational model fundamentally assumes that types exist. Relations are made of attributes, and those attributes obviously must have types. But the original relational model itself never actually defined what those types must be. It left a pretty big gap. The Third Manifesto steps right in to fill that exact gap, providing a detailed, comprehensive theory of types to perfectly complement the relational model. Types are completely independent of the relational model, yet they are absolutely essential to representing our complex reality, whether your type happens to be a simple integer, a complex audio file, or a geographic map.
So if SQL's historical baggage and logical loopholes totally disqualify it as a true relational language, what in the world do we use instead? Well, the authors define rules for a completely new language paradigm they simply call D. Now, D isn't a single piece of software you can go download. It's a generic name for any imperative, high-level language that perfectly conforms to the rules laid out in the Third Manifesto. In their book, they actually outline a specific educational version of this called Tutorial D, just to demonstrate the concepts in action. Instead of SQL's messy syntax and overlapping features, D provides a pristine, purely relational environment designed from the ground up for absolute mathematical accuracy.
To ensure that conceptual integrity we keep talking about, the manifesto outlines strict proscriptions. These are things that language D is expressly, absolutely forbidden from doing. For starters, there is no attribute ordering and no tuple or row ordering. There are absolutely no duplicate tuples allowed whatsoever, which preserves the mathematics of sets. And crucially, there are no nulls and no knowledgeological mistakes. A true relational database just cannot contain an attribute that simply lacks a value. It doesn't make logical sense. And finally, the most pointed proscription of all, D shall not be called SQL. These rules are put in place to explicitly filter out the bad habits we've developed over the decades, ultimately protecting the pristine integrity of the data model. Let's actually look a bit closer at why nulls are entirely banned, because it's fascinating. We have to compare two-valued logic with three-valued logic. True relational theory is based on standard two-valued logic. A proposition is definitively either true or false. But the moment SQL introduces null to represent missing or unknown data, it forces the entire system into three-valued logic: true, false, or unknown. Think about how chaotic this gets in practice. If a system doesn't know value A and it doesn't know value B, and you ask the database if A equals B, what happens? You get massive logical paradoxes. Standard mathematical operations begin to completely break down. This leads to queries that return logically incorrect results without even throwing an error, leaving you completely unaware that your data is compromised. The manifesto demands a strict return to two-valued logic by completely, totally eliminating nulls. Now you might be wondering, without using physical object pointers or IDs, how does a strict relational system know that one thing is a subcategory of another? How does it handle modern programming concepts like inheritance? Well, it uses a brilliant concept called specialization by constraint. It operates on a really simple three-step logic. Step 1. Types are sets of values.
Step 2. Subtypes are simply subsets of those specific values. Step 3. This system automatically enforces inheritance, based entirely on constraints applied to those values, rather than relying on physical pointers buried under the hood. It elegantly takes the very best ideas of object orientation and integrates them directly into the relational model, using nothing but pure value constraints. It's really quite elegant.
The grand concept that ties all of these rigid rules, types, and mathematical sets together is conceptual integrity. This term was coined by the legendary computer scientist Fred Brooks, and conceptual integrity is arguably the single most important factor in any system design. Brooks argued that it is vastly better to have a system that reflects one single coherent mental model than a system that contains a bunch of really good but entirely uncoordinated ideas. The Third Manifesto exists to fiercely protect the conceptual integrity of the relational model. By trying to be everything to everyone and patching over gaping logical holes with things like nulls and duplicates, SQL completely abandoned that integrity.
As we wrap up this explainer, I want to leave you with a lingering thought for the very next time you sit down to design a database or write a complex query. Really ask yourself, are you actually building a true logical model of reality, or are you just writing variables, relying on hidden pointers, and crossing your fingers that three-valued logic doesn't silently corrupt your results? The Third Manifesto makes an incredibly compelling case that we just don't have to settle for the deeply ingrained flaws of SQL anymore. By fully embracing true relational logic and strict type theory, we can finally build systems that are as logically sound, rigorous, and robust as the real world they are trying to represent. So, what kind of system will you build?